Do I have to use this? Probably not. Well, let's see how far we can go without microphone. So, as you probably recall from the last talk, I suggested that I provide some information on how to actually conduct these factorial studies. Most of the most important aspect of this methodology is to provide appropriate research design. So then, for that reason, I'll talk about two types of designs. One that involve and/or decision gates, and we call this disjunctive-rule signal structures. And after that, we talk about the novel signatures of a holistic or configural perception. And that answer that you can recognize somewhere here. Again, just remind you about general definition, general approach to a validity hypothesis. We say that objects are perceived as whole entities and not a simple sum of features. And we use kind of, in this point, maybe interchangeably with a configural perception. And the second one will be pitted against the analytic or feature-based hypothesis that the perception of object occurs at the level of a feature. So one way to learn about underlying processes is to learn how they are organized. What is their processing order, what is the stopping rule, what is dependency between processes. We listed those as fundamental processes of fundamental cognitive properties of elementary processes. And one way to learn about these processes is to apply system factorial technology. And as I said, there's a bit of history of application, of development of the approach, and then there's another, I would say, last 10 years we see pretty much explosion, if I may say, of the application of such methods in a different area. Here's a SFT design in a nutshell. That's from my recently accepted paper in Frontiers. Editor here is Cheng Ta. You know how Frontiers papers are very tough, to publish. You only have to provide enough money. But actually, there's a peer review process, and I just show you one excerpt from this paper. It's about SFT approach and what it makes. What is it actually? How do we use it? So let's say that you would like to learn about an n number of processes. So you believe that underlying structure, let's say you have n number of processes, just need to identify them. Then your design, because now it's all about experiment, the design should have n independent variables. And this is the first requirement. Let's say you think about maybe two processes that you would like to learn. One could be configurable process of eye separation. The other could be second order relational feature, such as nose and lips difference. Two features, configurable features, and we would like to learn how they're processed, how this information from processing these two features are combined together. Are they serial or parallel? Do we use stopping rule? What kind of stopping rules? Self-terminated, exhaustive? Are these two processes independent or not? So you need to have in the design two independent variables. So this is the first thing, at least two. So I'm talking about here a condition that requires at least a requirement. So now we have two independent variables, two processes, three processes, three independent variables. Now, second manipulation, very important manipulation, is to add saliency to this whole process, to the whole method. The saliency is operationally defined here as a manipulation. So there's a certain experimental manipulation that selectively influences a single process of interest. Yes? Such that the process will be speed up, and we call this H, high saliency, or slow down, in which case it's low salience. Right, so this is the second requirement. We have two variables at least, and we have to manipulate saliency of these processes. That means, again, if we have second order relational features like eye separation, we have to find eye separation that makes high saliency case and eye separation that makes low saliency case, at least. Right? Now if you combine the two, you have to combine them in a factorial fashion. So you have first order relation of the second order relation of features is eye separation that is on the manipulated level of low and high saliency, and you have the other feature, let's say nose position, nose to mouth difference, that is also manipulated at a low and high level. So this is factorial manipulation. That's why the name is system factorial technology. The total count now is 2 to the n. The total number of experimental conditions at least you should have in your design to learn about the fundamental properties is 2 on the power of n. Here n is number of processes, right? 2 comes from these 2 levels of salience. So if you'd like to learn about 2 processes, you need 4 conditions. If you would like to learn about 3 processes, you need 2 to the 3, which is 8 conditions. And so on and so forth. You see, if you increase the number of processes, our aspiration goes up, and the number of conditions really exponentially goes up. All right. So that is as simple as this. You have to follow these guidelines, and that's how you can arrive at a system factorial technology method. Again, what do we learn? Here we learn about different mental architectures. We learn serial terminating, we learn serial exhaustive, parallel terminating, parallel exhaustive, coactive. I mean, possible catalog of these mental architectures, maybe we can add more here. Maybe special architectures could be involved. We don't know that, but if you envision that you might be willing to investigate certain type of architecture, you may be able to find it. I doubt that I don't doubt we can include it here and then maybe find specific signature for that architecture. So this is how they are presented. Again, let's say these are 2 features, second order relation of features, eyes and lips all the time, but we see that here in serial order, and they can terminate here on eyes. You don't have to process lips, and that's OR gate. Yeah, this is called OR gate. Here we have serial exhaustive. You process both features, it arrives at end gate. So you sequentially process one feature, then don't make a decision, turn to next feature, analyze it, and then proceed to the end gate and then make a decision. Is that the phase that I know, or is that another phase? And so on and so forth. We have parallel system, parallel, so we process them in parallel, but the first one finishes, it's parallel terminating, or parallel first terminating process, as we used to define it here, and parallel exhaustive, which we have to wait for both of them, but in parallel occurs processing. Yeah. And this is the coactive. We glue together information of an identification of separate features into one unit. So instead of eyes and lips, maybe we have a combination of eyes and lips. Maybe someone's Joe's or Bob's, eyes and lips here. Like a grandmother cell, maybe exemplar, stuff like that. And then it feeds into the decision unit. All right. So these different architectures, we see that last time we given different labels because we started to think, okay, holistic, analytic, have different properties when we break down to this serial parallel stopping rule and dependencies. Yeah, this one, coactive, we believe it belongs to strongly holistic processing, because instead of dealing with the isolated features, we're dealing with the combined features. So on the right-hand side, these are different signatures revealed by system factorial technology. These are called driver interaction conscious function. Here, this function is flat. So see, at the moment, this is a signature. Yeah, so indicator. So if the outcome is a flat, then this is the underlying architecture. If the outcome is negative and positive with equal areas, then this is a serial exhaustive. If you have a positive function all the time, this is the parallel self-terminating. It is negative all the time, parallel exhaustive, and coactive has this negativity, but overall in a larger positivity expressed here. So different signatures of SAC. So that is very indicative, and you can see how different signatures will indicate different underlying mental architecture. So that's how we identify them. In a matter of fact, for the SFT, as I said, it's non-parametric approach in the SS. It could be parametric, but in this version, it's non-parametric, so you don't have to fit the results. if you use the guidelines from the previous graph, make a design, accumulate data and calculate these signatures, then you would say, without any model fitting, you would say, oh, this is what is going on underneath. Yeah, so, in matter of fact, within the SFT approach, there are two signatures used, and one is called a mean interaction contrast. Here, we didn't talk much about this one. It is also based on the double differences of, in this time, reaction times for these experimental conditions. They're pretty much low, 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 high, high, low. They correspond to different level of salience. If you remember that one, we have to have a low and high saliency of our factors. And then this is the first, and the second one indicates, in this particular case, could indicate maybe facial feature. Is it the first facial feature or the second facial feature? First process, second process. In this case, both processes are low saliency. In this case, the first one was low, and the second one was a high saliency. And what we find is mean interaction contrast, which is it is pretty much identical to what we use, to test ANOVA interaction test significance. To learn about the cognitive structures, the factorial technology uses this kind of full factorial design. And if you have two factors with two levels, we find this interaction contrast, and it tells you something about properties of processes. So these are different signatures used. Now, we didn't talk much about it, but the point is, the mean interaction contrast is also associated here. We have this mean interaction contrast is additive. If you remember additivity from ANOVA, here it's under additive, here is over additive. This mean interaction value is larger than 0, smaller than 0, here is equal to 0. It can be used also to predict or to indicate the presence of different mental architectures, here parallel, coactive, or stopping rule. That's another way, another signature maybe to investigate. Now, unfortunately, this one is not as good as the next one that we mainly discussed. This is about interaction contrast, in which instead of now means, here we have functions. So each of these conditions corresponds to one particular experimental condition. Remember that we have, in this particular case, we have two processes, two levels of saliency. That means 4 conditions. Let me count. 1, 2, 3, 4. Yeah, here they are, right? You find double difference, and because these are 4 functions, the outcome would be another function. This is a signature that we talked about. There's a mathematical correspondence between MICs and SACs. As a matter of fact, if you calculate integral of that expression here, integral of some other function will result in a mean value for the particular condition. So calculate integral of that function, the area under the curve. Here we get the MIC value and these means. So there is a correspondence. SAC provides better insights because it has better diagnostic properties than MIC. Because it's function, it provides more information than MIC, which is just comparing 4 dots. Now let me show you actually how do we do that in a simple terms. So let's say that underlying architecture that you would like to learn consists of 2 processes, but we don't know whether this is a maybe serial or exhaustive organization like this. So I just put it as an example. So let's say we have 2 processes and you find 2 manipulations that can affect only these 2 processes. This is called selective influence. So your control would be to manipulate process A with some experimental manipulation, and such that that manipulation will speed down and slow down or speed up that process of interest only. So this one will manipulate only A and not B. So maybe that could be removing the eyes from each other or something. Then you have to do the same thing for the second process of interest. So in another manipulation, it will affect only B but not A. This is our hope. Good. And then most of our experimental methods rely on this idea of a selective influence. This is a critical assumption in experimental psychology. So you find this manipulation, you propose 2 processes there. So what you have to do is you just have to combine these manipulations in factorial fashion. We have low, yes, in the case where both processes manipulated are somehow that they are slowed down. So maybe, for example, you put some mask over the eyes here, and mask, this is mask over the eyes, and if it is fast, you remove the mask. So that makes this fast slow. And maybe this is a mask over the nose, lips area. So when the mask is present, you have slow. When the mask is absent, you have fast processing. And that's, probably likely a good way to maybe deal with this whole design. So you can design when both masks are present, we have slow condition. You see, like this is one condition in experiment. And that's, factorially combining, orthogonally combine these levels. We got fast, slow, fast, and fast, fast. So your experiment at this state, at this moment, has 4 conditions. That could be, for example, designed like this. So you have 2-dimensional space. You have eye separation and lips position here. So in eye separation, you have 2 groups of faces. We call these jets. I mean, these guys are called sharks. As you can see, if you go along that dimension, eyes are more separated. So jets and sharks. If you go to this dimension, lips position, we see that lips are getting closer to nose. And let's say that as experimenter, you set up, this decision criteria, or somehow you impose this criteria by saying, well, look, these are the gang members and these are the other gang members, and then you are presented with one face at a time. You have to decide whether you're seeing sharks or jets. So press shark, if sharks, press left button, if jets, press right button. So how do we get, these factorial manipulations that we discuss here, as you can recognize HH, low, high, low, and low, low here. Now, saliency of these features is defined here by the proximity of that feature, to the, in these faces of that group, to the proximity to the other group members, the opposite group members. So the fact, that this distance between eyes is close to the opponent group member, you have to give a different response, make processing of that particular feature slower than that of that guy here. So this is a low level, and this is a high level. And see on the first feature, on the first dimension, high, low, we had a change. And the same thing across the other dimension. Do you see that now? This is one way to do it. The other maybe would be using masking. But I'm just offering one approach, to this manipulation. So high is the phase that is most salient on both properties. Eyes are most distinct from the other members of the process faster, and the lips are the most distinct when compared to the other members of their process faster too. But unlike this guy, which is because of proximity to these 2 opponent members, face members, both features are kind of slowed down. And that's how we get this factorial design. Now, so here is a Sabave interaction conscious function, right? So we have to find somehow a way from here to here. How do we do that? Now you just make this experiment, you isolate these 4 conditions, and you repeat this task many times with these faces. And you collect 4 different reaction time distributions. So these are density functions, frequency as a function for the reaction time pins. So reaction time distributions, and everybody's familiar with that. High, low, high, and doesn't tell much. It looks pretty much identical here. So what we do, the next step is we have to turn this into survivor functions. And so another step is also relatively simple if you're using SPSS or maybe some other statistical software. What you have to do is you have to press one button, and then this button will calculate first cumulative value for the numbers of trials for this reaction time distribution, and then we'll take the inverse of that, 1 minus that function, and we'll return this survivor function. So it's everything just a couple of clicks away. So there's not much to do. You don't even have to know what is the property of a survivor function in order to generate this kind of experiment. You only need to have design. You have to calculate. You have to collect reaction times, and then we'll find a way to find or estimate empirical survivor functions. Now I have this symbols here, ugly, but just ignore them and that. So do this for 4 times, and we see that each survivor function are corresponding to the observed data are aligned with respect to the particular expression here. Survivor function for this condition, survivor function for low, low, that's it. Survivor function for high, high, this is the survivor function. And we have to find the double difference between these 4 functions. plug in appropriate symbols here, minus, minus, plus, and the resulting function, boom, it looks like this. Now, what is this function? It's negative pretty much all the time. And if we go back to the catalog, we can identify it as a parallel exhaustive process. So that's one way to do it. Do you have any questions so far? Please, you can ask questions, or should I step back? Or I mean, this is an important step. I just wanted to show how this is relatively simple. It's not a booky, or doesn't even require much of mathematical understanding how this exact calculation works. Now, I'll just show you one case, two cases where we apply the SFP in the case where we have continuous stimulus dimension, where saliency is actually lying in a continuous dimension. And we take this configurable second order facial features, eye separation, nose position, and we show in these two cases conjunctive-rule stimulus structure, so-called OR and AND designs. So here it is. It looks maybe abstract, but we are not far away from the previous graph. Notice, that I repositioned these four members here. Then when you compare to the previous graph, but you can do whatever you wish, as long because you're the creator of the research design. In this particular one, these four guys will make this factorial design, and they pick up some values here on the eye separation dimension, which is kind of continuous value. Right here we have lips position, another continuous dimension of a facial property, and you decide, okay, these guys, for example, let's fit him against another guy we call hero, right? And so we have four guys here and one guy here, and this is a gang, and this is a hero. Your task is to, when one face is presented at a time, to say, do you see a gang or you see hero? Is it a difficult task, this one? Probably not. In order to learn whether, for example, when that face is presented, you can use two different rules. You can use two different rules to classify that face here, hero. Yeah? You can use this value on the eye separation as a criterion for decision making. It says, oh, look, I see the face, and the eye separation has value E3, and that's from the right-hand side of the decision criteria, that must be hero. So you don't have to pay attention to lips position at all. Likewise, you can do the same thing, for the other dimension, if you consider the first. This is the case when you process information in sequence. If you process information in parallel, first dimension that finishes will trigger the response. So this is why we said this approach, this OR stimulus, disjunctive category stimulus structure is analytic friendly. It goes well with analytic type of processing. You don't have to process everything. You can just process one phase dimension and you can arrive to the solution. All right, this is OR design. And you have to analyze only four cases, and analysis of four cases and calculate. It's a value function would tell you what happened really. We could expect, to see some analytic methods. Now here's another design. It's fairly similar to this one, except the position of the other group members are different. Now we have two guys here and two guys here. As you can see, these guys and these guys share properties with the target category on that dimension and on this dimension. So you can already imagine that this is a more difficult task. And why is it difficult? Because you cannot use a single rule to make a decision here. So let's say this face is presented here, the Jets member, this one, and then if you take a look, and let's say, oh, let's pay attention to eye separation. Oh, eye separation has value of 3, let's say maybe maximum, and probably you could say, oh, look, this is a Jets, So it's, in this case, this is a very fast decision. But if you somehow first pay attention to the lips position and read, this information, pay attention to that face, you say, oh, look, this could be any of these three faces that I met before. So I don't know which one it is. I have to pay attention to eye separation. So in some cases, you have to conduct exhaustive processing. You have to analyze both dimensions. So this is what we call this is holistic friendly. Holistic friendly, I just put quotations here because it's not really implying any holism. But you have to process all information in several cases. In matter of fact, in order to categorize target shark members, you always have to process all information. Because each of the shark members shares feature with the jets. Jets could be categorized, classified based on one property, but these guys have to be consulted in both dimensions. Otherwise, you cannot make a good decision. And that's called AND gate, because it refers to this target target. All right, so I show you this disjunctive and conjunctive stimulus rule categories. They are probably give rise to analytic processes here or holistic processes. We don't know what kind of processes actually we're going to see there. So here's another way maybe to look at it is a design that Joe showed yesterday, which we have, it seems like binary values of saliency of dots. Could be bright dot or dim dot or absence of a dot, And as a matter of fact, you see like it could look like AND design if you ask your subjects, oh, as soon as you see both dots, press left one button. If you see only one dot, regardless of the brightness, press the other button. They will generate directly AND design here, and you can use, this is exactly factorial group, you can analyze it to calculate SSE function. So another way to look at the OR design, again, here's the case, I position now the target group over here, ellipse position as a function of eye separation. We got all this saliency across different features. Here's a hero guy. You can make a decision maybe using this rule or that rule, or, it doesn't matter which one they use. So that's relatively easy to ask. Let me see what we found. In the experiments in a study that we conducted, we found that SSE for these three particular subjects were all positive, All positive, which one it is? And can you recognize signature here? That's right, it's a parallel self-turning. So processing there was parallel self-turning. And we expected that. It's analytic in a way because we can stop on seeing one feature. You don't need to combine features. You only have to analyze single feature. So conclusion, parallel self-turning mental architecture. Not really holistic process. People can be elated. How about the end case? Now this is the target group, the same thing here. Factorial, factorial manipulation, the two features, two saliency level high low. What happens? We have to use both rules here to classify these guys. Or maybe we can use coactive rule too. Coactive mental architecture. In this case, I'm not sure really that we're dealing with simple rules as presented here. But you have to process both information. So here's what we found. Participant 1, 2, 3. I can see this negative, the positive, negative, positive, negative, the positive. It's not maybe visible clearly by eye, maybe from the distance that you're seeing, but this positive part is larger than the negative part. So that is a signature. S signature, positive, larger than negative. And where does it find it here? It's not exemplary case, but you could categorize it as a coactive because it shows the smaller negative part in the larger positive category here. So we say coactivity. It's coactive processing. Interestingly, these subjects will report introspectively that they see faces after a while. They've been trained, to recognize these faces, and at the moment of test, they did like 20 sessions so far. So they showed really introspectively both coactive process. They saw entire faces, and they indicated in behavior report, to see indicated behavior analysis. There's a coactive mental architecture. So this is these are the two cases. Another way maybe to look at the task is target categories. Here, different faces, and we used similar design 2010 paper. These are the results in 2010. So, how would I stay the time? 30 minutes to go. Please ask me any questions. I don't want to sleep and to be bored or something. I would like just to share some information with you, and then eventually, if you're wrong,
when you analyze the RT data, you actually take all data, put a negative, one pie as opposed to say you separate them into different segments. Is there any indication? If there's any indication that we change the processing?
The answer is very simple. you're saying, how do we get these distributions? And then use fixed size bins. And you know what? You use 10 milliseconds bins, but there's no difference. You're using 1 millisecond. Larger the bins, get coarser information, which is not good. So better maybe to use even 1 millisecond bin. Will generate nicely smooth function over there.
But the question is, well, you put all the data together as one big packet, as opposed to say.
Yeah. So all these reaction times belonging from only seeing this phase here. This reaction time distribution is after recognition this particular phase here.
Is there a difference between like day 1 and day 2?
Oh, day 1, day 2. Well, you can always monitor for that to see if there are any learning effects, and eventually try to remove this learning effects if you're not happy with that, and try to also manipulate in the analysis to see whether there's any effect or not. Yeah. But you can do session by session. We did session by session. We didn't lump. If there's no big difference across sessions, then we just lump everything together.
In the example you're not discussing, the hero versus the candidate, you have only one sample for the hero.
Yeah.
And then for the graduate and game member, you have.
It does make, in matter of fact, in this particular design, this member will show up, 4 times more than these guys, each individual case. But you know what, you can add 2 or 3 more guys and make another square here. That would be like 2 factorial design. Sorry, two factorial designs. Yes, you would have another design here, another design there. So it's about a matter of the point is whether you can generate enough of the differences on these eyes and lips position dimensions, or whatever your property you're manipulating.
Chinkar raised an interesting point, which is that in the OR task, is it possible that people are memorizing the hero face and then just checking whether any of the features mismatch the hero face, so they're not actually applying the rule boundaries in the manner that you think they are, but are instead just trying to confirm that one of the features mismatches, which might be amenable to the parallel self-terminating process in a way which actually trying to use the boundaries in the AM task isn't.
I don't know. How do they? I don't understand. How would they compare?
So you have a template for the hero face.
Template for the hero face.
And then your task is just, does anything mismatch this hero face?
I would say, in this case, I would see not any of this recognizable signatures, but more something like coactive signature, because the template matching is not the same as a feature. It's a feature matching.
Oh, but the conditions that you're using to compute the SIC are not the template you memorized. So I see what you're saying.
Yeah.
So that you haven't memorized those.
Yeah.
You're just then processing, well, does anything look different from the hero face? And that's something you can possibly do in parallel self-terminating fashion.
I don't see a really big difference by comparing the entire face that has one feature different than using comparing feature by feature.
The context, though, is that's something you can do in the OR task, so it's still in parallel self-terminating, but you can't do that in the AM task.
Yeah.
So that might be a reason why the AM task is just too hard to do the parallel self-terminating.
Yeah.
Yeah, if you have too many jets, you can't memorize them all. Or you could memorize them all, but it doesn't help you do the task. So.
Well, ideally would be to position another 3 guys here and then have them a number of them balanced, so they don't go like that. Next. And then the next step is, as I mentioned last time, there are many. I'm talking about different signature, holistic perception or configural perception. I mentioned a bunch of different ways we operationally define holistic processing for different types of effects observed in experiments, pop-out effect, particle paradigm artifacts, square effects, phase inversion, unitization, camel phases. These are all different procedures leading to indication that underlying processing relies on holistic properties or configural properties. We see that Jim, Joe, and Daniel here mentioned different capacity index, in different forms they could use, and I talked about this co-activation signature. The question is, yes, so this particular experiment, when we use end research design, as an particle paradigm. We show the superiority of recognition of features within the all phase context. You'll see like this is faster and then less accurate, at least with corresponding to this condition. But generally you see faster processing when you analyze this particular mean reaction time using SIC. We see there's a co-activation signature spread there, so it gives nice, interesting support that something holistic is going on here. Then we published this in the science paper. The question was, can we provide a validation, better, a stronger validation of such a signature? Yes, and I propose here, and together with Daniel, we propose dynamical SIC signature. So as we can probably before see, that there's a catalog of the signatures of SIC signatures, which are mainly static. Yeah, they don't change. They're just one frame of information captured across maybe sessions or experiments. But here we propose dynamical SIC signature. And the signature that I'm having in mind that will kind of adopt, snake wiggle, maybe for the time on more appropriate dragon wiggle or something like that. So what happens here is we can see that there's a SIC function, yes, SIC function that starts from this stage, yeah, it's negative at the beginning here, and you can see it starts protruding and rearing, showing its head, above the line, at a certain point. So that's the signature we propose as another, should be maybe aligned together with a hall of fame of different operationalization of a holistic process. So, snake wiggle. Now let me just give you one more maybe view of what's happening here. This simple, I don't know how to get them. But anyway, the analysis was break down by sessions, session 1, 2, 3, 4, and plenty of sessions. Subjects, as they're practicing this task that I just described, and task with the phases, at the beginning show this negative SIC function. See? And we know from the catalog that indicates parallel exhaustive processing after session 7 and 8. But something started to happen afterwards, and the function started to change its shape. Still could be cataloged as a serial. Here, if you see, this is a or maybe even coactive here, negative part and positive part of approximately similar or very close similar areas. And then here's a negative one, some change of shape, positive, and ends up pretty much in positive. So what we see here is transition from negative function to function that is S-shaped, so mainly positive part. And this is how it looks again. See how it starts to wiggle. There's a form here.
The reaction time we've got here, is it an absolute value because 50 is very short, or is it a relative value to something else?
Times 10. So this is a manipulation in order to get this times 10. So this is 2017. I'll show you the mean reaction time for this particular experiment. So it's extremely short. It's not like one of your super fast recognition experiments. This one is relatively slow. Yeah. So yeah.
So how many trials are there in each session?
There are many trials in per session. Because we combined here 2 sessions. So there are at least 200 or maybe 300 trials for every one of the frame per condition, and there are 4 different conditions, as you remember, because it's 2 factorial experiment, 2 levels, 4 conditions. Yeah, there's plenty of trials here. It's pretty stable. The very interesting is that most of the subjects show similar change of shape. The dragon wiggle, is not only associated with one subject presented here, but the other subject will show similar transition. Now, there's another property that worth paying attention is that you see like you start from negative, then the area is around here, the total area of the SSE function is negative, and then if you progress into the practice, it becomes positive, and a pretty high R squared here, so this is a very transient. So there's one regularity here. Another thing that happens is if you look overall mean reaction time trend is going down, and errors too. Both reaction times are faster. So if you're going from the parallel exhaustive to what we believe is coactive. We see a speed up in processing recognition, and the errors are going down to the level of this is less than around 4 or 5%. So we have another indicator that subjects are speeding up. That maybe that was previously used as a indicator of unitization. Unitization is similar effect that we use to indicate holistic processing, or maybe to indicate object perception, switching to maybe better object perception from analytic, because what happens, you're speeding up in processing, probably because something is going on, you're more efficient, right? And it may be something unitized. In this case, the phase will be unitized. So that's another signature that you're picking up. So here's a summary. Let's see function wiggles, from a negative to actually positive function. All subjects wiggle. That is very interesting. Yes, all subjects wiggle in the same fashion. The final stage was coactive, and when tested later on, subjects showed this coactive signature. Some of them did not. But they stopped at certain intermediate point. There's a performance superiority, mean reaction time and accuracy both were improved. Suggesting maybe kind of a unitization effect going on. Introspection also revealed the subjects are reporting seeing faces. Before that, in the first sessions, they were probably thinking, or maybe here, they are reporting, paying attention to features and using certain rules, and after a certain time, they are reporting, I start to see faces. Yeah, I just did think that on my MP3 player. Some of the subjects are just exactly very interesting report about that. So all in all, we say that the snake wiggling indicates, the holism, that is a holism that is built up, for maybe analytic type of processing. Can we learn more about it? So yeah, there is another indicator that could be used maybe to support the argument that is a there is an increase in holism going on. Here, remember that before we pay attention to these target categories, here, but now additional analysis to be published in a paper with Daniel and Rafalsky indicated that these phases, we call them contrast group phases. Contrast group are exterior and interior phases. When comparing them, we can also indicate a change in their architecture as an additional argument, as a converging evidence. In matter of fact, this is what is predicted yet to be concluded, in certain conditions that reaction times when we compare exterior to interior, remember, will indicate serial model parallel exhaustive, they're equal, they will indicate parallel contributing model, they're coactive, indicate, coactive processing. So comparing these two guys could also be used to another indicator of underlying processing. So what we're expecting to see in this particular case, as they progress to learning, actually will be coming from here to here, from this particular mode, because we saw parallel exhaustive here, to the coactive one. And if you look at the evidence, this is exactly what happens. We find the difference between external phase minus internal phase. On average, we see that there's an increase in this difference, going to the positivity, to the indicator of the holistic, the coactive signature. And that when we average across all subjects, got a similar trend with a changing of maybe shape at certain points, but pretty much, copying, the same, showing that this increasing, always monotonic increase into coactivity, indicated but now different signature. So see this as a converging evidence to support the original conclusions. So how can we explain this snake wiggle? Yes, how can we explain? Well, we believe, there's in your mind, I believe if each one of your minds or brain, maybe there is something like a machinery that can be used to amplify holism in a perception. I don't think it's really consciously regulated, but some other maybe system needs help. What can happen is, you can put yourself in analytic mode and start to pay attention to phase features. But you can maybe, with a little bit of effort, increase the amount of holism here, and then start to see glued features occasionally to the level where you can see entire faces. So I would say there is some mechanism that regulates, this behavior, so we can start to pay attention to features, or we can also switch to features, to faces, whole faces if needed, so it comes better, if you're meeting with someone or discussing to, see his whole face, not paying attention, the nose and eyes and that kind of stuff. Maybe it will be also a tidy way, right, to see entire holistic person, not as a set of features. So this is a possible model parallel system, which we have a feature processor one, first feature, the second one is an accumulator of evidence. It gets some information. When the information reaches threshold, it goes to the decision gate. The same thing happens with the same feature. So that will make a parallel exhaustive system. But it's grown in a more fancy way than before, right? We have, it looks like a system for electrical engineers. Where does it come? Where does it holism? Comes in maybe a potential use of our system. It's between crosstalks between these units. Now these red lines indicate there's a crosstalk. So when you get some evidence from the facial feature 1, it's been sent to the facial feature 2, and that speed up in accumulation of evidence in the opposite feature. So if this is a well-learned phase, the two will help each other, and we can see this gluing, building from a parallel system to something that looks like coactive, positively facilitated mechanism. Here's the stuff that I propose, we harbor somewhere in our brains, that you can actually turn left or right this knob and then change this level of cross channels facilitation between these two facial detectors. So again, let's me summarize it. The last thing we propose is snake wiggle, dynamical signature of system factorial technology, surviving interaction contrast function that can indicate that through the learning there's a typical path to coming to holistic processing. So instead of providing freeze frame of current status of your processing, it shows you how it changes over time in a regular fashion. We see that signature is actually there's a converging evidence for that to believe actually that this change is transition from analytic to more holistic processing through superiority effect, the robustness it happens across many participants, maybe robustness in other processes. But in the introspection terms are also indicating that something is going on there. The entire stimulus set, wiggles, so it's not only one subject that we find. Most of them, show the typical change. The possible model here would be the model dynamic accumulation. Then we talk about this model actually in the previous paper. It comes very handy, to be used to understand similar phenomena. And then let's wiggle, that's my final, so we can hold it around them. That will conclude, my presentations. If you have some questions, I'll be more than happy
to. How does the capacity change as a function of practice?
I don't know that, but that would be good, maybe a follow-up experiment in which we would be able to track down what happens with the capacity of the learning of the trial sessions. I did some investigation some times ago, but I'm not sure, that I can pull this up, for this particular signature. Yes. I don't think we designed the end experiment capacity function at the time, so we would really be, careful, to make the conclusion. But there would be good follow-up experiment maybe to do with the test capacity. There will be maybe another converging evidence, for the entire thing. Yes.
In your example, snake freeze, the snake freeze example, am I right that the coagulation that takes like the average of all your RT data from session 1 to session 8?
It's not the average, it's breaking down to different sessions. So the dynamical signatures is
Yeah.
that happens across learning sessions.
Yeah, but I mean, the conclusion, in the end,
Yes,
coagulation.
yes, that's my conclusion.
So I just wondered that is there any constraint on the history of the session? So the wiggle part, and is there any property that in some condition, in some cases, it's impossible to get certain kind of sequence and then come out with the correct coagulation conclusion? There's some mathematical constraint.
I don't see any mathematical. We just use the same set of assumptions that we use for the regular factorial experiments, except we add variable of training or exposure to the task. So you can see through the learning what happens and how the signature changes of the learning. So I don't see any other constraint in that there.
So you mean this regularity, this pattern is always like that?
Yeah, that's what we found. Across many participants, the patterns will change in the same fashion, from overly negative to mainly positive. Well, I have to say that some subjects, at least one, never reached positive, but were somewhere around zero. So kind of halfway between. Maybe the subject did not develop any holistic processes and decided to stay within the area of analytic, which is still manageable in this task. We can analyze these spaces using analytic techniques. But what if you get certain kick later on and you start to using these holistic properties because you learn these spatial features, so it's getting much easier. You got this boost in processing. It's probably much easier doing the task.
In other stuff, it's not the features of other stuff. It's like this time, whether we get a coagulation process with the session, you always look like.
I would say yes, because for example, this effect of speeding up can be achieved in many ways. And speeding up and increasing accuracy across sessions can occur just because maybe your passing processing, your overall rate increases without the change of the mental architecture. So maybe you're processing serial here, and maybe you're processing serial here, but just faster serial. We don't know that because this one doesn't tell you anything. It just tells you it speeds up. And speeding up can be achieved in many ways. Maybe here we are too cautious, or not too cautious, probably because there are too many errors, but maybe we couldn't see the features well, and maybe in a serial system, and maybe see features much better here, but we still process in serial. And if that is right, we should be able to see a serial signature here and a serial signature here, but this is not what we see. We see change, and we see the typical change in the machine. So that's why I say that's much better analysis, because it provides you more information what happens with the processes in terms of processing order, stopping rule, and dependency.
The dot patterns, for example.
I would like to use the dot patterns too, yeah.
Yes. So.
I didn't use it, before, but yeah, I would love to use it, yes.
More extensions, if like 3 features to 1 features, but or and will also have this kind of testing.
In the essence, I believe yes. If we believe, if you develop in the holistic properties, then this is what should happen. Signature with the 2 features here, because we believe features here equal the number of processes. With the 3 features, you have 3 different signatures. Now that's another story.
Yeah. Because that is the configuration of the different features, or just the one very basic mental processing for all tasks to back tasks.
We don't change, there's no change here in the type of logical rules used to process the task. You have to analyze these phases using AND rule in all cases. So, but that's good, because then with these changes, we do not explain by changing the logical rule. The only thing they could use to explain these changes is actually change in the architecture, in the mental architecture. And what kind of change? Well, we provide some converging evidence that it is actually coming from parallel to coactive. It doesn't switch actually in terms of the parallel to serial, or probably not, but we believe it's parallel from the beginning, and then it builds up, this fast limitation between units. That would lead, to the change of the signature will go through first type to the coactive type, the parallel type, parallel exhaustive to the coactive type.
I'm sorry, we have to stop here because we last talk, we didn't like this. So possibly we have more patients, so we can do that. Sorry about that. Sorry about that.
That's okay, thank you.
Go ahead.
So, no stop. Let's begin the math talk given by